Welcome to topic number 16 in Richard James Mathematics Resources. This topic is entitled Statistics. In the list of my resources for CSEC students, this is number 16. However, it is the 41st and final one to be presented. This is by no means an indication of its importance. This branch of mathematics is the most widely used. There are two branches of statistics: descriptive and inferential. Descriptive statistics is a branch that makes use of data collected, which are most times not in any useful form. The data is arranged in order, sometimes placed in tables, and devices like graphs and charts are used in order to make it easier to be analyzed. Inferential statistics use the data in order to draw conclusions about the system on which the data was collected or a similar system. There is no doubt that large corporations, banks, hospitals, and schools make use of statistics, but this alone does not contribute to its widespread use. When you were in primary school, your classmates asked you how much you got for your lunch money, and on hearing the answer said, "That is why you are so fat." That was the use of a single statistic to come to a conclusion. When you entered the 7th grade in high school and wanted to play football on the team, the coach asked you how many matches you played in primary school and how many goals you scored. He wanted to use the information solicited in order to make a prediction as to how likely it is that you will score goals in the upcoming competition, which is making use of inferential statistics. We are going to begin our presentation on statistics by making mention of measures of central tendency. The measures of central tendency in statistics are the mean, mode, and median. The mean is found by adding the entries and dividing the result by the number of entries. The mode is the entry that occurs the most times. A data set may have more than one modes. The median is the entry that is in the middle of the data set after the items have been sorted, that is, arranged in order. If the set has more than one middle entry, as in the case of an even number of entries, the median is found by adding the two middle entries and dividing the result by 2. We therefore find the mean of the two middle entries, and this will be the median. What are measures of central tendency really? A measure of central tendency is a single item of data that might be present in the set, or the members of the set may be manipulated in order to calculate that measure of central tendency. It is a single item or a single what we call parameter or value that gives an idea of what the overall set is like. Sometimes we choose the number that is in the middle of the set, and for some data sets that is a representation of the entire set. Sometimes we choose the one that occurs the most, and under certain circumstances that single entry is a very good representative of the entire set. And of course we use the arithmetic mean, which is found by adding all of the entries and dividing the result by the number of entries. So those central tendencies represent single items of data that may be used to represent or give a picture of the set or the information in the set on a whole. So we are going to find the mean, mode, and median of the following sets of numbers. Now, for the most part, this is going to be revision because these things have been presented from GSAT, and of course, students would have taken a look at these things throughout the lower school from 7 to 9 grades. So we are going to find the mean, mode, and median of the following sets of numbers. So the first one, to find the mean, add all of the entries and divide the result by the number of entries. So there we have all of them being added, and we are going to divide by 10. The computer would have calculated that for us. I hope that the value is correct. So we have, when we add all of these, we get 35. And we divide 35 by 10, and the result is 3.5, and that represents the mean. Now, we are going to take a look at the mode. We are going to look at this. We have 2 2s, 3 3s, 3 4s, and 2 5s. So the entry that occurs the most, we have 3 3s and 3 4s. Therefore, we have 2 modes. The mode is the entry that occurs the most times. We have 3 3s and 3 4s. We therefore have 2 modes. And we write them down, separate them by a single comma, 3 and 4. Those are our modes. The median is the middle entry. We know that there are 2 of them because the number of entries is even. Of course, we have 10 of them. Now 10 divided by 2 is equal to 5. And remember, we have 2 middle entries. The middle entries are the 5th and 6th entry. So let us see 1, 2, 3, 4, 5. So the 5th entry is 3, and the 6th entry is a 4. So we have 3 plus 4 divided by 2, and that is our median. Median is equal to 3.5. When there are 2 middle entries, the median may be found by adding them and dividing the result by 2, which of course is actually finding the mean of the 2 of them. And we are going to take a look at B. To find the mean, as usual, I'm repeating that, add all of the entries and divide the result by the number of entries. And when we add them, all of these numbers are added, and of course we have 1, 2, 3, 4, 5, 6, 7, 8, 9 of them. So when we add them, the result is 63, and we are dividing by 9. So the mean is equal to 7. And of course, the mode is the entry that occurs the most times. 7 occurs the most times and is therefore the mode. Of course, we have 3 7s. The other entries are fewer in number. So, the median is the middle entry. There are 9 entries. 9 divided by 2 is equal to 4.5. The middle entry is therefore the 5th entry. So 1, 2, 3, 4, 5. The 5th entry is a 7, that is the middle entry. Therefore, the median is equal to 7. We could have identified the middle entry by using the primitive method of simultaneously striking off pairs of entries beginning at the ends. So if we take off those 2, then take off the 2 that remain at the end, take off the 2 that remain at the end all the time. The one that is left is the one that is going to be in the middle. That is our middle entry and will therefore be our median. 7 is left and is therefore the median. This is a very large data set, we think. Now, I'm going to be using our typical way of finding especially the mean in order to show the necessity of having what we call a frequency distribution. So we are going to find the mean. I hope you do not think that I am crazy enough to add those numbers individually, especially when we have so many repetitions. Let us make use of the fact that we have 2 4s. Right? 2 4s are going to be contributed. That means 2 times 4. And of course we have how many 6s? 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 6s. How many 5s do we have? 1, 2, 3, 4, 5. So we have 4 5s. And of course we expect 8 6s. And if we count the number of 7s that we have right there, we'll get 10 7s. And how many 8s? 7 8s. And 3 9s. 1 10. Right. Now, if we had to do this and to put the addition sign between all of those numbers, the screen would not be wide enough. Right. And we are going to divide that by the number of entries. We may also be systematic about finding the total number of entries. We know the number of each. We will therefore add those numbers. So instead of saying that we are going to look here and count these, as a matter of fact, it is not going to be impossible for us to do that. But we are just establishing some principles here. We are establishing the principles by using a data set that is small enough to manipulate on the screen and to show the necessity and of course how the formulae and also methods that are used to manipulate frequency distributions. We are using this small enough data set to do it. But when the data set becomes very large, it is not going to be convenient to count the individual items in the data set like that all the time. So we are going to demonstrate the method that we are going to be using to do that. Now we know already that we have what? 2 4s. So we know that we have 2 entries for that. And we know that we have how many 5s? 4 5s. So we're going to have what? 4 entries for that also. And the number of entries contributed by the 6s. How many 6s do we have? 8. The number of entries contributed by the 7s. How many 7s do we have? 10. The number of entries contributed by the 8s. How many 8s? 7. So we are going to be adding the number of each entries, and that will give us the total number of entries. And that makes a lot of sense, especially when the data set is very, very large. So, of course, this 2 multiplied by 4 that we have here is this one. So we are just working these out and we are putting the answers there. And then of course 4 times 5 is 20 and 8 6s 48. And then we have 10 7 70, then 7 8 56, and we multiply them and we have a much shorter string of numbers to be added than if we chose to use the numbers individually. And of course we just add the denominators, so we find the sum and we get 35. When we simplify that, we get the sum of all the entries, which is the sum of the numerator that we have there, will be 239, and that we are dividing by the number of entries, which is 35, and that will give us our mean, which is 6.83. So let each entry be a value of the variable x. What are the entries? Take a look on the other slide. The entries are we have 4, 5, 6, 7, 8, 9, and 10. Therefore, let each entry be a value of the variable x. So what are the values of x? That's what we looked at on the slide when we just did our little recapping. So we have 4, 5, 6, 7, 8, 9, and 10. Those are the values of x. Those are the entries that we have in the data set. And of course, we know that we don't have to repeat them because we have their frequencies. So let the number of times each value of x occurs be its frequency, f. So let's repeat that. The number of times that each entry occurs is its frequency. And we know that how many 4s do we have? 2. Right. And we have 4 5s, 8 6s, 10 7s, 7 8s, 3 9s, and 1 10. So those are the frequencies. Those numbers are the numbers that tell us how many times their respective item occurs. The mean is x bar and is written as, that's what we call it. Some people call it bar x because the bar is above the x, so they call the bar before the x. I call it x bar, and it is perfectly safe to say x bar. So x bar is equal to, what do we do? It is equal to the summation of the products of f and x. Remember, that's what we did? We added all of these products. All of the products were added. Right. So we are adding all of the products of f and x. So that's the summation of the products of f and x. And then we are going to divide that by the summation of f. This means summation. It is, as a matter of fact, the capital Greek letter sigma, and it means the summation of. So when you see, especially it being used in statistics, and it is also used in pure mathematics, especially when we are dealing with sequences and series, we always use sigma, and it means the summation of. The data may have been better placed in a table with the values of x and their associated frequencies. And the table with the values of x and their associated frequency is called a frequency distribution. This is better for manipulation and analysis. So what do? We put the values of x right there. And of course, we put also the values of f. In finding the mean, let us multiply the values of f and x as before. Of course, 4 times 2 is 8, 5 4 is 20, 6 8 is 48, 7 10 70, 8 7 56, 9 3 is 27, and 10 1s 10, as before. But this time it is easier in order, and it is easy to determine what we have done. We have here x and we have f, and we have fx. Just tells us that we multiply the values of f and x. We may continue by finding the sum of the values of f and the sum of the products of f and x. So we are going to put the sum of f right here and the sum of the products of f and x right there. And of course, x bar is equal to the summation of fx over the summation of f. As usual, as before. These values are not strange, so we may just write them down as they are. The mode is the entry that occurs the most times, and hence is the entry associated with the highest frequency. So the largest number in the frequency column is 10. So if we are going to find the mode, we are going to see or try to find the one with the highest frequency. We find the highest value of frequency, which is the largest number in the frequency column, which is 10. And its associated x value is 7. Therefore, the mode is 7. The median is the middle value. There are 35 values. 35 divided by 2 is 17.5. The middle entry is therefore the 18th one. So, we have 35 values. 35 divided by 2 is 17.5. The middle entry is therefore the 18th entry. We are now in search of the 18th entry. At the end of the first row of the table, we would have passed 2 entries. How do we know that? Because the frequency is 2, telling us that we have 2 4s. So at the end of right here, we would have passed 2 entries. So we have the second one. We would have passed the second one right there. So as we traverse the table, going down, right there, the other row has 4 entries. So we pass an additional 4 entries. So therefore, by the time we pass the second row, we would have passed the 6th entry. So in here, we have an additional 4 entry. So we're going to add that to the 2 that we have there. So we would have passed the 6th entry. An additional 8 entries in the next row, right there. So if it is in addition to what we had before, at the end, we will have the 14th entry. So we have 8 entries in that row, and it's of course an additional 8 entries. Therefore, we need to add the 8 to the 6th, and we'll have the 14th entry. So at the end of this row, we'll have the 14th entry. Then we'll have an additional 10 entries there, and at the end 24. So we'll have the 24th entry by the time we have passed this row. So this one ends with the 14th entry, and this one ends with the 24th entry. And we are in search of the 18th entry. The 18th entry must be in the slot that is between the 14th and the 24th entry. In that slot, between the 14th and the 24th. So the 18th entry must be in this slot. Therefore, all of the numbers that we have here are from entry number 15 to entry number 24, because this one ends at the 14th entry. So we know that in here we are going to begin with the 15th, from the 15th to the 24th. Therefore, if we have the 15th, the 16th, the 17th, all the way to the 24th here, we know that the 18th entry is in this slot, and all of the entries in this slot are equal to 7. Therefore, the median is the value of x that is inside of this row, and the median is equal to 7. We'll move merrily on to grouped frequency distributions. If the range of values in the data set is wide and the number of entries is considerably great, it would be appropriate to divide the range into suitable and, if possible, equal sized portions called classes. The range of marks is divided into classes as shown, and those are the classes in blue. So we have classes from 10 to 19, 20 to 29, 30 to 39, 40 to 49, and those are the classes. In each class, the smaller number is called the lower class limit, and of course we're going to use this for the short representation, LCL, lower class limit, and those are the smaller numbers and those are the lower class limit. And of course the larger number in each class is called the upper class limit, UCL, and those are the upper class limits. The formula that we use for the ungrouped frequency distribution may be used to find the mean of the grouped frequency distribution. The drawback is that we cannot multiply f by all of the values in the class. We need a suitable value. So we need to find f times x, the product of f and x. But, of course, the data we have in this class will go from 10 to 19. So we cannot multiply 5 by 10, 5 by 11, 5 by 12, and so on. So we need a suitable representative of the class, or a single value that will represent the class. And here is our clue. The value that is appropriate is the midpoint of each class. That is found by finding the mean of the lower class limit and the upper class limit. So we're going to find the mean of the lower class limit and the upper class limit. The lower class limit for this one is 10 and the upper is 19. 10 plus 19 divided by 2, we get 14.5, and that takes its position right there. Also, 20 plus 29 divided by 2 will get 24.5, and so on. Notice that we have a pattern right there. 40 plus 49 divided by 2, 44.5 also goes there. We may use the trend to complete the column. Right, so we can just take advantage of the fact that we have 14.5, 24.5, 34.5, 44.5. We can see a trend. We are always going up, adding 10 each time. With the midpoints being the values of x, find the product fx as usual. So we're going to do fx as usual. So we have the computer doing every single one of them for us very quickly. 14 times 54.5, 10 times 64.5, and so on. In your own good time, when you have 9 months in which to be prepared for the examination, you may take as long as you want to find those values of fx. But we have to present this in a matter of minutes, so we'll have to make use of the technology. The summations of f and fx will be calculated and placed in their respective places. So we are going to find the summation of f, and it will go right here. When we add that, we get 100, and the summation of fx is 5060. So the mean, which is given by x bar, is equal to, as usual, summation of fx divided by summation of f. So x bar is equal to summation of fx 5060 divided by summation of f, which is 100. And the result is x bar, the mean, is equal to 50.6. Our next assignment is to find the median by constructing a histogram. A histogram is a bar graph that is used to represent continuous data. As such, consecutive bars must be joined. So if there's a continuity or a continuum, and we are using the histogram, which is a bar graph to represent data, since the data is continuous, the bars are going to be joined together to show that there's a smooth and easy transition from one class to the other. If the first bar begins at 10 and ends at 19, and the second begins at 20 and ends at 29, the bars will not be joined because the number 19 that ends the first bar is not equal to the number 20 that begins the second bar. Therefore, we have two bars, 10 to 19, 20 to 29. This is the first bar, or representative of the first bar. This is representative of the second bar. Now, the bars will not be joined together because this one ends at 19, the next one picks up at 20. We need to find a common boundary that will be shared by the first and second bars. The number most logically should be halfway between 19 and 20. So this is the end of the first 19 and the beginning of 20. I think they should join hands halfway. It is obviously 19.5. So if we're going to go halfway between 19 and 20, we know that is 19.5. But we may calculate the result by doing what? Adding the upper limit of the first class to the lower limit of the second class and dividing the result by 2. And we get 19.5. Now remember, that is a boundary that is going to be shared by the first class and the second class. That means it is going to end the first class. So if we have it ending the first class, it must also begin the second class. So we have what? Ending of the first class, beginning of the second class. Then we go to the other class. The number that ends the second class must be the number that begins the third class. And of course, they are going to join hands halfway. So we'll have 29.5 and 29.5 to begin the third class. And of course, if we want to be mathematical about it, we are going to say what? 29 plus 30 divided by 2, and that is equal to 29.5. So that is going to end the second bar and begin the third bar. So the third bar is slated to end at 39. Here, it is ending at 39, and the fourth bar to begin at 40. So this one ends at 39, this one begins at 40. So what do? We join halfway, 39.5, to end the third bar, and 39.5 to begin, of course, the fourth bar. But by the time we have done that, what do you notice? We have a pattern. So we may use the fact that each subsequent item may be found by adding 10 to the previous in order to complete the table. And we may just run through the table like that. No problem whatsoever. These numbers represent the shared boundaries of the bars to be placed in the histogram and are appropriately called boundaries. The smaller ones are the lower class boundaries, LCB, and the larger ones are the upper class boundaries, UCB. The boundaries are not limited to the use in constructing histograms. They may be used in any situation that makes use of the common ground between classes, and of course there are other relevant situations that we may use boundaries in. The lower class boundary of the first class is missing. As we can see, there's a slot missing in the table right there. So we are going to count the lower class boundaries down, say 39.5, 29.5, 19.5. What do we realize? We are going down by 10. So the next is going to be 19.5 minus 10, which is 9.5. And it goes right there. And our table is completed. So, of course, we are going to plot, or we are going to construct our histogram. In constructing the histogram, the first bar will begin at 9.5 and end at 19.5. and its height will be 5. So this bar begins at 9.5, ends at 19.5, begins at 9.5, ends at 19.5, and the height is halfway between 4 and 6. It is 5. So it goes up to 5. And of course, the next bar will begin at 19.5 and end at 29.5. So because this bar ended at 19.5, now this one will begin at 19.5. So we are sure that they are joined. So the second begins at 19.5 and end at 29.5, and its height is 7. The next bar begins at 29.5, ends at 39.5, begins at 29.5, ends at 39.5, that is close to 40, and the height is 18, all the way up there. And this one will have a height going up to 26, beginning at 39.5 and ending at 49.5. So it begins at 39.5, ends at 49.5, and the height will go all the way up to 26. Our next assignment is to find the mode by constructing a histogram. A histogram is a bar graph that is used to represent continuous data. As such, consecutive bars must be joined. If the first bar begins at 10 and ends at 19, and the second bar begins at 20 and ends at 29, the bars will not be joined, because the number 19 that ends the first bar is not equal to the number 20 that begins the second bar. Now, we are talking about continuous data. Now, if we are talking about continuous data, then our device that we are going to use to represent it must show that there is a continuity. Now, if we are doing things in a continuum and we are talking about bars, then the bars being separated will show discontinuity. Therefore, the histogram has to have the bars joined together. Of course, the first bar begins at 10 and ends at 19. The second bar begins at 20 and ends at 29. Because 19, where the first one ends, is not equal to 20, where the next one begins, then we are sure that the bars will not be joined. We need to find a common ground called a boundary that will be shared by the first and second bar. The number most logically shall be halfway between 19 and 20. Therefore, there we have, this is where the first one ends, this is where the second one begins. So we know that because we are going to be representing the information by using a histogram, the bars will have to join. So what would be the most appropriate number to join between 19 and 20? I think halfway between would be quite logical. So it is obviously 19.5. But we may calculate the result. So although halfway between 19 and 20 is obviously 19.5. But, of course, we can use calculation to show that. 19 plus 20 divided by 2 is 19.5. Now, when we get this value 19.5, what will that be? It is going to be the boundary, which is the upper one, or the one that ends the first bar, and it is going to be the one that begins the second bar. So we have it indicated here. It will be the one that ends the first bar and the one that begins the second bar. And we need to do that again. So this bar needs to end at a figure that is convenient between 29 and 30. So it will be that number which is halfway between 29 and 30, which is the most logical point for those two bars to be joined. So of course we can do our calculation. 29.5 will be our answer. 29 plus 30 divided by 2, that's 29.5. So the end of this second bar is going to be 29.5, beginning of the third bar. And of course, if we continue, what do we know? This bar that we are going to have right here, 30 to 39. It is better that we have it ending at a number that is going to be shared between 39 and 40. And we are going to add 39 and 40 and also divide the result by 2. So 39.5 will be the most logical point. Of course, by now, we can see a pattern developing. So we may use the fact that each subsequent item may be found by adding 10 to the previous in order to complete the table. So instead of working out every single one of them, we can establish a pattern that we have this bar, this column going up by 10 each time, and also this one going up by 10 each time. And we can fill these columns out in a matter of seconds. These numbers represent the shared boundaries of the bars to be placed in the histogram and are appropriately called boundaries. The smaller ones are the lower class boundaries, and we are going to write that in brief by calling it LCB, and the larger ones are the upper class boundaries. We are going to shorten that by calling it UCB. Boundaries are not limited to the use in constructing histogram. They may be used in any situation that makes use of the common ground between classes, and of course they may be used in other relevant situations, because there are other situations that just make use of the boundary between classes, but they are relevant to statistics. Lower and upper class boundaries may also be used in those situations. The lower class boundary of the first class is missing, and we can see that we have that blank rectangle right there. That's where it belongs. And of course we can just look right here and see how it goes down very nicely. So the lower class boundary of the first class is missing. If we count the lower class boundaries, say 39.5, 29.5, 19.5, we will be going down by 10 each time. The next one will be 9.5, and that's what our first lower class boundary will be. Now we are going to use the information to construct our histogram. Of course we have, this is our frequency axis and this is our marks axis. And of course the lower class boundaries and the upper class boundaries are descriptions of the marks that we have in our initial table. As a matter of fact, in the first column of our initial table, what do we do? Our first bar will begin at 9.5, end at 19.5, and the height, which is represented by our frequency, will be 5. So this is what we have. That's our bar. So that is our bar, beginning at 9.5 and ending at 19.5. Now the other one will begin at 19.5. That is where the first one ended, of course, so that the bars may be joined. And will end at 19.5. And the height of it is 7. So we expect it to go up somewhere about right there. Right. So it begins at 19.5, ends at 29.5, and the height is 7. Now we move merrily to the other one that ends at 39.5. So it begins at 29.5, where the one, this one, or the current one ends, begins exactly where it ends, and it will end at 39.5, and the height of it is 18. So it will go all the way here like that and go down like that. So that's the bar. What about the other one? Begins at 39.5, ends at 49.5, and the height of it is going to be 26 all the way up there. While drawing the histogram, we are always going to be aware, because of the pattern in the numbers, of where the next bar is going to be. Well, more appropriately, where it is going to end, because as long as we have drawn the first bar, the second bar will begin at the same point where that bar ended. So we need to be more mindful of the height of the bar more than anything else. And this one will go up to 26. This one will go up to 14, beginning where the previous one ended, and it will end at 59.5. So that's our 14 bar. And this one will end at 69.5, beginning where the previous one ended, and its height is 10, as we can see there. And of course we have two 10 bars, one next to it, right? So that bar will begin at 79.5, end at 89.5, and its height will be 6, as we can see. And of course the final bar that we have will begin at 89.5, end at 99.5, and its height will be, of course, 4. And that completes our histogram. So we have our lovely histogram. The modal class is represented by the tallest bar. And that's our tallest bar. To find the mode, first draw a line from the upper right vertex of the modal bar to the upper left vertex of the bar on its left. Well, so we are going to draw a line from here to there, which is the upper right vertex of the modal bar, and it is going to come right there to the upper right vertex of the bar that is on the left, like that. And we're going to draw another line from here to there. After that, we're going to draw a broken line from the point of intersection of these two lines, and it will meet the Marx axis, so we can find what the mode is. So that is our dotted line. The mode is at the point where the line touches the axis, so the mode is right here. And if we read that value of the Marx axis, we should get 43.5 in an accurate diagram. Information stored in the computer is digitized, and so is the computer display. This means that it is not possible to place information at every single location on the screen. Sometimes the position where it is desirable to place a line is not available. The line will therefore have to be placed at the closest available position. This takes away from the accuracy of the diagrams that are constructed. For example, the lower boundary of the first bar seems close enough to 10 to be at 9.5. So we intended this one to be at 9.5 right here. That's what we intended to be. But the upper boundary, which is this one, that should be at 19.5, we notice that it's some greater distance away from the 20. So we know that it is not quite 19.5, but should be a little less. Sometimes in a statistics problem, we are asked the width of the class interval. It is natural to say that between 10 and 19, or between 20 and 29, we will have what? 19 minus 10 is equal to 9, or 29 minus 20 is equal to 9. So we have 19 minus 10, that's 9, 29 minus 20, that's 9. and we could say that is the width of the class interval. This may be the case because in a set problem, only the class limits are given. So like we have right here, the class limits are given. And that is how we usually have problems given, with the class limits. So if we are going to just jump and find the width of the class interval, quite likely we are going to say 19 minus 10 is 9 and 29 minus 20 is 9. With the understanding that although data is given in limits, as we have them 10 to 19, 20 to 29, 30 to 39, etc., marks that fall between 19 and 20 must be catered for. So any marks that will fall between 19 and 20 has to be catered for. The width of the class interval, WCI, is more appropriately calculated by using the class boundaries instead. In any data set, the class interval that we are going to calculate must cater for the numbers that are between the two classes. It must cater for the numbers that are between the two classes. So we have what? It must cater for the numbers between 19 and 20, and between 29 and 30, and between 39 and 40. So the width of the class interval must also be calculated in order to cater for those numbers. So the width of the class interval is going to be calculated by using the boundaries. So we are going to be using what? 19.5 minus 9.5, and that is equal to 10. And of course, we are talking marks out of 100, percentage. So the width of the class interval is therefore 10%. The width of the class interval will be used extensively in more advanced statistics. It will play a very important role when finding approximations for mode and median of group distributions without the use of a histogram or cumulative frequency curve. When we are not going to be using we will not use the cumulative frequency curve nor the histogram to find the median or the mode respectively. Knowing the width of the class interval, or even more importantly, knowing how to calculate the width of the class interval, is going to be very important. Continuing, next we will construct a frequency polygon. A frequency polygon gives a pictorial view of the distribution of the data throughout the set. The highest point is the region where most of the scores accumulate. It is in that general region that we will find the mode. If the distribution of the scores is close to what we call normal, then the mean and the median will also be very close by. So anywhere we find the mode in a normal distribution, the mean and the median should be close by. As a matter of fact, statisticians assume that they are equal. Many situations in advanced statistics require that the distribution is normal, that is, has its maximum at the middle and taper off towards the extremes in a special way. A general term that is used for a normal distribution is a bell curve. There is one bell curve that has special characteristics. It is called the standard normal curve. In solving many statistical problems, scholars usually assume an analogy between the distributions and the standard normal curve. The frequency polygon is the most rudimentary form of the normal curve. So, the frequency polygon that we are about to construct is the most basic form of what is known as a normal curve. And of course, we have a standard normal curve, which we will take a look at in more advanced work in statistics. And we assume statisticians, in order to make calculations, make predictions and all of that, and also to classify members in a data set, they use the normal curve in order to do that, and they assume that the data that they have is analogous to a standard normal curve. So all we need to do now is to construct our frequency polygon because that's the most basic form of the normal curve. In constructing the frequency polygon, we will plot frequency against the midpoint of the classes. The midpoints were calculated when we were finding the mean, if you could remember that. And of course, we have them right there. So we're going to just plot the midpoint with the frequency. So 14.5 will go with 5. So we have for the x value or the max value 14.5 and the height will be 5. For the other one, we will go out to 24.5 on the x or the max axis and the height will be 7. And our x will go right there. And for the other one, we go to 34.5 and the height is 18. And we are going to put our little point right there that we are going to use at the end. And 44 is our max value. So we go to 44 and we go up all the way to 26 and we put our x right there. And we are going to move merrily on to 14 for the frequency and 54.5. So we go to 54.5 first. Then we move merrily up to 14 and we make our mark right there where the point should be. And we have the first of our pair of tens. 60, let me see what it is, 64.5. So we go to 64.5 and then we go up to 10. And the other one will be at 74.5 and its height will be 10 also. Well, 84.5 and we'll go up to 6. And finally 4 and its associated max value is 94.5. So we go to 94.5 first and then we go up to 4. The frequency polygon may be completed by using straight lines to join consecutive points. That is how we construct our frequency polygon. But what do we know? After joining the points as we have them, the structure may not be left hanging in the air like that. For one, it would not be a polygon because it is not closed. It has to go down to the max axis. But where? Where on the max axis will we cause it to go down? The values of the midpoints will give us the clue where to put the line down to the axis. The left leg should be anchored where the midpoint of the previous class would have been. So if we are going down the sequence, we are going down say 34.5, 24.5, 14.5. The next value is 4.5. So we need to meet that axis at 4.5. And where do we put the right leg? We put the right leg where the midpoint of the subsequent class will be. And of course, if we follow the sequence, 74.5, 84.5, 94.5, we'll put it at 104.5. Right there. So that completes our frequency polygon. In this case, we will be finding the median of the grouped frequency distribution by drawing a cumulative frequency curve. In this case, we will plot cumulative frequency against the upper class boundaries. Now we are seeing other uses of the boundaries except for drawing a histogram. In the interest of space, we will leave out the irrelevant columns from the table. So we're not going to include all of the columns from the table. As the word suggests, we are going to accumulate the frequency. The first item in the frequency column goes first. So we are going to start with 5 and then we are going to accumulate as we go along. So the present item in the cumulative frequency column is added to the next item. So the present item, which is this one, in the cumulative frequency column is going to be added to the next item in the frequency column in order to generate that one. So we have the 5 and the 7. We'll add them and we get 12. Then what do? We go to the present value in the cumulative frequency column and we add another frequency value to it. So 18 plus 12, and that is going to be equal to 30. 30 goes there. Then we go what? To 26 and we add that result to 30. Then we go to 14 and we add that result to 56. Then we go to 10 and we add that result to 70. And we do that until we have completed our table. Finally, we add 4 to 96 and we get 100, and it goes right there. We will proceed to plot cumulative frequency against the upper class boundaries of the marks and complete the resulting curve. So that's what we are going to do. We are going to plot as usual. So the cumulative frequency is 5 and the upper class boundary, which will represent our marks, 19.5. So we go to 19.5 and we go up and we put our mark right there. Then we go to 29.5 and then we go up to 12. And of course, we have a color code showing that the upper class boundary will be on the axis that is accompanied by the red arrow, and the cumulative frequency will go on the axis that is indicated, or whose direction is indicated by the blue arrow. And we continue. 49.5 for the red, that is on the marks axis, and we go up to 70. And we continue going up all the time. So what do we do for the other one? We go to 69.5, and then what do? Go up to 80. And then at the end, we mark our X, and then move on to 79.5, go up, mark an X, 89.5, and we go all the way up to 96 this time, and we plot. And of course, the arrows are indicating exactly what we are doing, and we are following the color code that is given in the table also. Then we are going to attempt to draw our cumulative frequency curve. The curve cannot be left hanging. We'll have to cause it to touch the axis where the upper class boundary of the previous class would have been. So that is how we do it. We are going to cause the curve to touch the axis, but it is going to touch the axis where the upper class boundary of the previous class would have been. And if we go down like this, notice what we are going to do. We are going down 39.5, 29.5, 19.5, then 9.5. So it will touch the axis at 9.5. So that is our cumulative frequency curve. The first, our lower quartile, and of course we are using our cumulative frequency curve to do some necessary calculations. So the first, our lower quartile, is Q1. It is associated with a quarter of the total cumulative frequency. A quarter of 100 is 25, so we go what? Find 25 on the cumulative frequency axis and draw a dotted line across until we reach the curve, like that. Let's go to 25, draw the dotted line, then when we get to the curve, we draw a line down. So we draw another dotted line down to the marks axis. Right. And that value that it touches the axis, which is 38%, that is our first quartile. The median is our second quartile and is associated with what? 2/4, which is a half of the total cumulative frequency. What is the total cumulative frequency? 100. So a half of 100 is 50. So what do? We find 50 on the cumulative frequency axis and draw a dotted line across until you reach the curve. So go to 50, draw a dotted line until you reach the curve. What do? You draw another line that goes down to the max axis, like that. And that value is our second quartile, which is the median. So the median is 48%. Of course, there's another one. The third or upper quartile is Q3. It is associated with 3/4 of the total cumulative frequency. 3/4 of 100 is 75. So find 75 on the cumulative frequency axis and draw a dotted line across until we reach the curve. So 75 and draw a dotted line across. When we get there, what do? Draw another dotted line that goes down to the max axis. And that value that we have there, 66, is our upper quartile. In addition to measures of central tendency, other very important parameters in statistics are measures of spread. Some of them include range, standard deviation, variance, interquartile and semi-interquartile ranges. While it is important to know, on average, how well the class performed in an examination, the analysis would not be complete if we do not have an idea of how far, in general, the scores are from the mean. The measures of spread supply us with the information. So, although it is very important to know on average how the class performed, if we do not know or have an idea how far the marks are in general from that average score that we have, then we can be misled. Quartiles are markers in a data set that divides it into quarters. As such, we need 3 markers. So one is going to be in the middle that divides it into 2, and then we have 2 more dividing the halves into 2 other parts. The standard deviation tells us on average how far each item in the data set is from the mean. Arriving at the standard deviation is somewhat more tedious than arriving at the quartiles. However, almost all elements in a set falls within 2 standard deviations of the mean on either side. So if we have 2 standard deviations on the left and 2 standard deviations on the right, therefore we have 4 standard deviations in all. And we have 4 quartiles in all. So this makes the semi-interquartile range a rough approximation of the standard deviation. So the interquartile range is given by Q3 minus Q1. And we remember Q3 65 and Q1 38. So the interquartile range is the difference between the two, which is 27. And of course we are talking about marks out of 100. So we are talking about percentages. So that is 27%. The semi-interquartile range is given by Q3 minus Q1 divided by 2. But we know what the interquartile range is already. It's 27. So we divide that by 2 and we get the semi-interquartile range, which is 13.5%. All students should have an idea how to find simple probabilities. Probability theory is in the primary school curriculum. We will take a look again at finding probabilities. The probability that an event will occur is given by the formula. Probability is equal to total number of events that will give a favorable outcome over the total number of equiprobable events. On the next slide, we will be required to find the probability that a student gets less than 40 marks. The total number of events that will give a favorable outcome is equal to the number of students who gets less than 40 marks. The total number of equiprobable events is equal to the total number of students overall. This is equal to the maximum cumulative frequency. So the total number of students overall is equal to the maximum cumulative frequency, which is 100. So let us do that. Go to 40, we are going to find the probability that a student gets less than 40 marks. But we need to find out how many students get less than 40 marks. So go to 40 on the marks axis and draw a vertical dotted line to meet the curve. So that's our vertical dotted line that meets the curve from where marks is equal to 40. So we need to find out those who get less than 40. So we have to find the associated cumulative frequency value. So draw another dotted line across to the cumulative frequency axis. So we are across to the cumulative frequency axis. The favorable region will be indicated by the red arrow, and there we have our red arrow. But not a surprise, because we need the number of students who get less than 40 marks. So when we go over to the cumulative frequency, we have to talk about the region that is below the marker. And how many students are below the marker? The number of students involved will be from 0 to 30. This is equal to 30 minus 0, which is equal to 30. So those students in this region. So 30 students. So what is the probability? The probability of getting less than 40 is 30 over 100, and we may write that as 3 over 10 or 0.3. The probability that an event will occur is given by the formula, so we are taking a look at that formula again. The total number of events that will give a favorable outcome over the total number of equiprobable events. On the next slide, we will be required to find the probability that a student gets more than 70 marks. The total number of events that will give a favorable outcome is equal to the number of students who gets more than 70 marks. Again, the total number of equiprobable events is equal to the total number of students. This is equal to the maximum cumulative frequency, which is 100. So go to 70 on the marks axis and draw a vertical dotted line to meet the curve. So we'll go find those who get more than 70 marks. So if we are going to find out who get more than 70 marks, we go straight to the marks axis, go to 70. What do we do next? Draw another dotted line across to the cumulative frequency axis. That is our other line. The favorable region will be indicated by the red arrow. Notice that that favorable region is from 80 to 100 because we required those who get more than 70 marks. So when we get to the cumulative frequency axis, we are going to deal with the region that is above the marker. So the number of students involved will be from 80 to 100. This is equal to 100 minus 80, which is equal to 20. So the probability is going to be 20 over the total, and that is equal to 1/5 or 0.2. The required number of students are those who get more than 70 marks. The favorable region must therefore be above the marker as we had it. On the next slide, we will be required to find the probability that a student gets between 30 and 60 marks. We will use two vertical lines at 30 marks and at 60 marks because we need to know the number of students who gets between 30 and 60. So we need two vertical lines, one at 30 and one at 60. As such, we will need two corresponding lines that meet the cumulative frequency axis. So two vertical lines, then we are going to need two corresponding lines. Go to 60 and 30 on the Marx axis and draw lines to meet the curve. So there we have the two of them. They meet the curve. And then draw corresponding lines across to meet the cumulative frequency axis. And that's not very strange. We have done that on two previous occasions, only that we had single lines going up in each case. The favorable region will be indicated by the red arrow. That's the region. That's between the two markers. The number of students involved will be from 10 to 70, and this is equal to 70 minus 10, which is equal to 60. So the probability is 60 over 100, and that is reduced to 3/5 or 0.6. In graphical questions, students do not usually get the exact same answer. No need to worry. Graphically obtained values are not expected to be accurate to the last dot. They are usually considered to be approximations. If your answer is not as expected, ensure that it is the one that you arrive at from your graph. If your graph is incorrect, you will not be penalized a second time for results obtained from it. So, if your graph is not accurate, the values that you get from the graph are still the values that you need to use, because you will not be penalized a second time for it. This presentation is by no means the sum total of all that is required to be learned in statistics. I have copies of the CSEC papers from 1989 to present, and I have seen a pie chart only once, and that is on the 2008 papers. This means that the examiners are not ruling anything out. Students need to know statistics from the GSAT level all the way up to the 11th grade in preparation for the CSEC exams. Being aware of this fact, I am encouraging prospective examination candidates to use this slide presentation in addition to the things that they have learned from what? GSAT all the way to grade 9 and beyond. I must also take this opportunity to apologize for the crooked appearance of the cumulative frequency curve that we had. And of course, we explain about how the thing on the screen is digitized, and we cannot possibly put what we really want to put at a particular location, because sometimes the exact position is not available. But we sometimes get these defects because of the digital nature of the available positions on the screen. If students are able to use that curve in the learning process, that would mean the world to me, even though it is crooked. Richard James has presented mathematics for over 20 years, and he has never tried to be perfect, as you must have realized from previous presentations. What he has used all of his energies to do is to get students to learn. There is a smoother representation of the cumulative frequency curve, but it is not pertaining to the data that we have just done. Your cumulative frequency curve should be as smooth as the one that you have right there on the screen.